All right. Here is what we're going to be doing for the lab today, later on today, which is we're going to be looking at Vega Light. Vega Light is wonderfully, oh, there's, yeah, Melanie's in the background there. Say hello to everyone, Melanie. Anyways, what we're going to be doing today is dealing with Vega Light. I got Kara was brave enough to finally to contact me and ask how to fix up some of her D3 stuff, and we were looking at loading in a JSON file in D3, and then I realized, oh, the reason I stopped doing that or didn't do that is because it's a royal pain. At least you can do it in Vega Lite, and it's actually handled in a more elegant way. Or it's, both are elegant ways, but one requires a lot of overhead, a lot of setup. For D3, it turns out, just in case anyone was interested in this, for D3, you need to actually load it into a real web page and have run a remote server, which I'm not going to ask anyone to be doing for at least for a lowly little assignment. So the reason is because it will not allow you to asynchronously load. It asynchronously loads, but it has to load any external files that are in the same location on a server, not locally, because otherwise it's a security risk. So that's the reason why it's in the file, in the JSON file, in the JavaScript file itself. In case you wonder what I'm talking about, it's this thing right here. Right here is mine, and I'm just showing you answers because I don't really care anymore. You guys are. This is for practice for you guys to be exposed to this, not because I want to terrify you. So here is me putting in the JavaScript itself. I'm putting in the data manually. And what I could have been doing is trying something like this. This is actually traditionally what you might have done, which is I'm loading in a JSON file, an external JSON file, instead of in the code itself. But then I need a callback, because one of the things about D3 and JavaScript in particular is everything's asynchronous. You have no idea when things are coming in. You have no idea when, if you're loading in an external file, you're loading in an image, whatever the case is, you don't know when that's coming in, which leads us to all of this kind of stuff. So enter append. I'm going to change my attribute, and I use a function to do so. Why? Because I don't know when it's coming in. That's the weird thing about JavaScript. That's why everything's built around this kind of callback mechanism with all these function calls everywhere inside of another function. I can't guarantee at any time, essentially for this entire thing, I don't know when I'm getting that callback. I don't know when that file is being loaded in. I don't know when, let me think of another, let's see another example here. I don't have that many great examples in here, but there's a couple of them in there. Whenever any of these events happen, I don't know when they're going to happen. I have to do it asynchronously, as in I don't know when these things are coordinated. And so my programming style is radically different from most other languages. In C, you do line by line. Yep, you certainly can. Let me finish the one thought. C, you normally do line by line. JavaScript, you say, it's going to look somewhat like this. We're going to have a bunch of callbacks. And it's all callback based. Yeah, Tori, go ahead.
Sorry, can you hear me?
Okay. Yeah, I guess got to turn it up a little bit.
Yeah, sorry. I just wanted to ask because I didn't want to like interrupt you with my voice. And for my question, please like let me know if I'm understanding anything wrong. But if we look at the like the enter block of code and you're looking at the attributes, from what I understand from JavaScript, the D in parentheses after the function is like, okay, you're taking in a variable here, right? Mm-hmm. So I'm just curious as to which variable is that referring to? Because for the longest time, I was trying to take in two variables because I thought the X and then the year from the array was two, but it only works with one. So I'm just wondering which variable is like being taken in, which one's like not a variable.
This JavaScript still to this day, I keep on thinking about this and realizing I've learned JavaScript like 5 times and I've forgotten. I've purged it from my head. I think PTSD thing 5 times. Let me just try and point out something here. Where is this X? Well, we've seen it somewhere else in here. It's up here. But it's not, it is a variable, it's doing something. it's a slightly different beast. And I should have probably pointed out that gory detail in here. That is a mapping. Essentially, it's a lookup table like the Dewey Decimal System. That's at least my understanding of the whole thing. And I could be wrong about this. I'm not a JavaScript expert. I haven't been doing it in industry for years and years and years. And most of the time when people get good at this, it's because they've been doing it. It's not like they've learned it in school and then they become experts. It's they get their hands dirty in industry. But this is a mapping. So I go from this domain, which is 2010 to 2016, this data range, to this data range between 50 and 350. So if I have 2010, it might be 50. If I have 2011, it might be 75. You know, if I have 2012, it might be 100. Like it maps from one of these things to the other one. And so if I put in the year, what ends up happening is it goes in and it pops out another value. It maps one to the other. Like cosine of 30 gives me another value, right?
Okay.
So this is acting like a function. Some input and it spits out an output. The x itself is not a variable. It's variable up here. It's a global variable, but it's the mapping. It takes in data a year and spits out some other value. What you're seeing here is this is an anonymous function which takes in some data input d. What we're saying here is where is d? D is actually defined in, well, we can look at the actual your real code that you guys are looking at. So here we go. Here's a return value. Okay, so every time I have anything of type circle, you'll notice that I have some variable d somewhere. Where's my d? I'm loading in my data. Here's my data. It's called weather. Every time I load in data called weather, and I set the attribute. So for all the circles, it has certain data. So when I set the attribute, it uses the data d, whatever d is. It's just a local variable here called d, whatever kind of data I have. So it's from the weather value, the weather information here. So this is effectively d.
Okay.
Well, sorry, for each row, it will be the value d will be this, or it'll be this, or it'll be this. It's one line at a time. And then I say that d at the year. Oh, in this case, for the first line, it's going to be this thing. It's going to, so it'll be 2010 for the first time. And then the next time I call this, the function calls again, and the d.year value is going to be 2011 and 2012 and 2013. It's taking one row at a time, and the d is one of these rows each and every time. That's essentially what's happening here.
All right. Okay. Thank you. Thank you so much. That makes a lot more sense to me now. Thank you.
And it's one of those things I get scared. It's like, what is this thing doing? Yeah. Especially the y coordinates where everything gets flipped around. Notice that this is another one of our mappings. This is some kind of mapping between, this is just a color map. So this is the kind of color, we'll look at that today, where you pass in some value and it tells you a color. In fact, and this is what this thing here is. I have multiple different kinds of functions. One of the kinds of functions I can have is it takes in some data and it takes in the index, the count number. There's also functions that take in data and take in an error message. And if I get an error, I can handle the error. Oh my God, this is so loud. Okay, so I'm so sorry. We're trying to support local business, but we cannot leave the room here because we don't want to be anywhere near the clean people. So here is a function which takes in a d and it spits out and it takes in an I, which is our counter, and then I can do something with that counter. That's another way we could have done that. So I could have put a di thing here as well, and it should still have worked. But since I'm not using that I don't want to write it that way. Oh my God, she's loud. Okay, so hopefully that makes a bit more sense. We can also go over that again in the lab. And I'm going to smack my wife. She's loud. Okay, so I don't know if it's too loud for you guys. Hopefully, you're only hearing me, but if you're hearing her very loudly, I can go and poke her or something like that. So that is what I want. I just wanted to point out what we're doing later on. Here's what I wanted to go over first. So Thank you, because she's very distracting to me. This is what we did last time. And here's the thing I would like to point out. I've looked at your images right now and I love them. I want to spend, I'm not going to, but I would love to spend the entire class going over all these images and having you explain things. Some of these are awesome. Some of these, have room for improvement, but I'm very proud of a lot of the stuff you guys passed in. It was very nice work. So some of them are, we can work on some of the details. So I'm just going to blow through a bunch of them and we'll see what we have here. So yeah, you'll have to turn your head. So we have the design was Crystal. So maybe you, Crystal, you can also type it in if you want. What are we seeing here? And why are you showing this as the data? What's the task? If Crystal's on here. You don't have to do the microphone, but you can if you want. Is Crystal even on here? May not be. Let's see. Nope, Chris is not on there. So we're going to move on. I'd like to. So my only issue with this is not what them collecting data. It's what is this going to serve as a purpose? How is this helping? So that's one of the, and by the way, reading handwriting is going to be a bit of a challenge. So if I misread names or anything like that, please bear with me. But this is just saying how many hours they're looking. But the person already knows this. Can the visualization help them? Is the question. So whose is this? I don't know who this is. This is characters on screen. A number of times the laptop was closed. Okay. So Tori, what's going on here? What's the domain?
Okay, it's coming back to me now. I watch The Office, and sometimes I find the scenes so absolutely cringeworthy that I can't get through the episode. So what we're documenting here is which character was on screen at the time at which I closed my laptop because I couldn't get through it, and we were marking like if there's a trend in a certain character, and there absolutely is. His name is Michael Scott. Yep, Isaac, you got it. I can't with him a lot of the time, so that's what we were documenting.
That's awesome. I love it. Right? And there's something that you're hoping to glean from this, like who is a cringeworthy character that you cannot watch anymore? Because yeah, we had trouble watching The Office too. We want to love certain shows. Even Modern Family is pushing us a bit too much. Where it's like, yeah, God.
Yeah.
Very nice. I like it. All right. Crystal stakeholder here. Xingpeng, what are we talking about here? Are you on? You can type or you can speak, whatever works. And are you even on? This you could do something with, right? If you're trying to figure out what your diet looks like, that's sorry, Crystal, who's not here. I'm picking on her anyways, but that's a little bit of a scary part of the diet, right? I need to know this. Like, how much Quebecois food am I eating and how bad is it for my health? I need to know these things, right? I have too much salt in my diet and too much, crap. We're trying to insert more salad. But you can infer certain things. This, I'm not sure what you do with, right? That the person already knows and perfectly fine. It's a great visualization. The task, I'm wondering, because you're trying to figure out, I'm not sure if you're going to infer anything new that the person doesn't already know. Does it help them with a particular task? Perfectly fine visualization. It's simple right now, but maybe it's the time of day when they practice. And that tells you something about what's going to motivate you to practice more often. That could be something that you could be looking at. I love this one. Great requirements gathering, great looking at what's being played, playing basketball in China, it's half court game and who's the king of the court, but maybe you're looking for who you can do a pickup game with who you find annoying as hell, who you don't want to play anymore. Not just the stuff you already know, but we're trying to tease out the stuff that might be useful for you in either reflection or you for make a rush decision when you're playing a pickup game of basketball. And you're like, oh, now that person's a jerk, right? So whatever the case is. And it's a nice initial approach to the visualization. I also, yeah, I always find it fascinating that a Canadian, well, the person who, one of the people involved in it was Canadian. So Canada connection for basketball. And Kara, I know I get you talking a lot, so I don't want to spend too much time about what? Or Will, actually. Will may be able to talk about this. What's the dinosaur about? So this is dinosaur lectures watched last week. Is there
Okay, so yeah, we had a midterm on Monday for the dinosaur class, and Will joined the class late, so he had to binge a ton of lectures. So the numbers were only 2 and 1, so I just drew a dinosaur and colored it in because it's cute. But there's like a pretty thick lie factor if you look at area instead of height. But like, I don't know, it's like not that serious. So I just colored in a dinosaur.
like the Monday, you'd think that's a lot longer, a lot more because the area is larger, despite the fact that you're talking about the height here. But yeah, what programs the dinosaur class in?
Oh, we're both just taking it as an elective. It's with earth science.
So is it a bird class are we talking about or?
I wouldn't say that.
Okay.
It was, yeah, it's fun, but it's a lot of information. But dinosaurs are cool. Okay, yeah, Will said the midterm was easy. I thought it was like
dinosaurs
mediocre.
are cool. I will give you that. And yeah, it's a nice change of pace from programming classes. I just was curious because awesome rainbow dinosaur. Although we're going to talk about rainbow color maps and how much I despise them, by the way. I want to go through a lot of these. Standard bar chart, perfectly fine. You can actually, for your fantasy hockey games, great use if that's something that's important. Not a whole lot of bars in the bar chart, but at the same time, where are you going skiing? I guess you can go to Quebec for snowboarding nowadays, but although I'm going to bash snowboarders here, and I want to know how long you're spent sitting on the hill versus actually snowboard. Every time I see snowboarders, they're like teenage snowboarders, not good snowboarders, but like people just learning to snowboard, they're always just sitting on the hill. I was like, I'm a skier, so I always like bashing snowboarders. Good. I have some friends that are phenomenal snowboarders, and you're like, oh, that's what it's supposed to look like. Okay, not the person, the poser on the hill. And absolutely beautiful, beautiful. Who was actually doing this? Whoever did the drawing in here, do the drawing for your group later on because I don't know, stylistically, it's really, really pretty. Oh my God, playing Hades, like maybe this is one of those cases where you're figuring out, oh, I'm wasting a lot of time playing this video game versus another. Just FYI, I mean, I may have already told you this story. I almost didn't get into grad school because I was spending all my time playing Neverwinter Nights. I said I'll play for an hour while eating breakfast, and then looked around and went, why is it suddenly dark? Oh, I played all day. Whoopsie! I have to do my letter for my grad school. That was when I learned I had a problem. Okay, dance train. By the way, acrobatics. I'm somebody whoever's doing this, you gotta let me know what the acro is for. Um, that's awesome. And I love this as well. It's steam weapons, torpedoes. This is Star Trek, right? Sebastian, and for Halkun's data. I'm loving this, right? Anything else? I mean, this is exactly what we're looking for, right? This is a somewhat unorthodox, and that's the point. Oh, number of times spent each day on hobbies. The other graph. Oh, this one here. What's acro then?
Well, I like it.
And very pretty, by the way. Yeah. Okay. But acro what? That's not the name of the dance. I'm assuming. Well, I want to go through the rest of these because I need to go through colors and stuff like that. Okay, great. But nice work. This, fantastic work. I'm loving all of these things. Like, look at this. Notice the banding here. What do we get with this banding? Oh, that little white band tells us where these levels are. Because we collect and perceive edges. Remember those bipolar cells and the mutual inhibition that we get for cells, that these bands really stand out as a result, right? And so you can see different banding, and now we have different colors for here to here, and so we actually see levels beyond a certain point. If something is extreme, for example, we can show a lot of different things with something as simple as a bar chart. So for P3, be creative, explore what you can do, swing for the fences, as it were, right? And then you can, pull it back later. But I want you to be open to just trying something crazy and new, not just, I made a bar chart, I made a pipe. You can do some really crazy things here. Okay. For example, by the way, how do you have 3 hours a day to work on TikTok? So I don't know how time intensive looking at TikToky talks. I have no idea what TikTok is. I'm an old guy. I don't use it. I don't have time to use it. I miss the Twitter trend, let alone the TikTok trend. So, but you do get a pointillization bar chart, right? Each one of those things, it's a counting task. But though it gives you a bar, it's a nice alternate way, and you get to brand it with the TikTok icon logo, which also conveys the meaning. It's really nicely done. I'm trying to figure out what the fingers are. So if you have anything on the fingers, that would be great. Whoever's this is. This is a TikTok thing?
I believe she went through how to do the report that she does for me on a monthly basis.
Okay, good enough. Right? But great, these are all great. Look at this. This is fantastic. Right? And we have parallel coordinates, and we're trying to figure out how much you're paying in these various shoes over time. And like 5 pairs of Nikes. And by the way, you have about 20 times more pairs. My wife calls me a shoe horse because I have 3 pairs of shoes. So that tells us where we are in our family. Engineer and a computer scientist. We have modest fashion inspirations, but I'm sure. What's her name again? Michelle Wolf will be very proud of your sneaker collection. Very nice, guys. So I want to get going on what we're doing. That's exactly what I was looking for. Very nice. I'm going to lock it down soon, by the way, in case anyone's trying to submit these things later. But I was very impressed with what you did. Make sure both names are on your submissions. No, there we go. So we're going to look at color perception one more time. Hopefully we'll get through all of color, maybe a little bit even into cognition. And we'll see why I hate rainbow color maps. I hate them. I hate them. I hate them. They do have a purpose in some places, but not many places. Okay. And we've been screaming into the wind for a while. Everyone loves putting them in there, and everyone in the research community goes, "Oh, hell no." Okay. In case anyone know what the background is, by the way. Who's a nerd? Let's see. I thought somebody would have nerded out on this one. Oh, okay. No nerds in the group. That's the Radiohead album In Rainbows. I have the vinyl, if you believe it. All right. So we were talking about color, and one of the things is get it right in black and white for a reason, because black and white. Well, we'll see today. The point of what I'm trying to aim for here today is lightness to darkness. The luminance value encodes data one way, or encodes information one way, whether you want to believe it or not. And hue colors it, encodes it a different way. And we're blissfully unaware of this as well. So this is what this thing looks like when I go to black and white. It also, if you do it right in black and white, it means you avoid problems with red green color blindness, which is another thing we'll look at today. So if you can cover all those cases by just making sure it works in black and white, and if you can add extra stuff, great. But it has to work in black and white first. It would be like, I don't, maybe this is a bad analogy or something like that, but actually we could do it with video games, right? If if your thing works on, your code has to, or your video game has to work on an old kind of computer, maybe say a computer from 5 years ago. If it works better on a newer system, great. But you shouldn't need some hot top of the line rig in order to run your this video game, and just to get anything out the door. You should have a low fidelity version of it for people with a modest system, and then you can increase the resolution or make it go at a higher frame rate with better graphics, whatever the case is, and ramp up the scaling. That's what you'd expect from a video game. Because if you don't get that, you get games like Alice, which is an old 20-year-old game, but it was so badass at the time that no one would buy it. It died on the shelves because no one could run it on their system, essentially. It was another 2 or 3 years before the average person could just put it on their system. And by that point in time, no one was really caring about it. So we talked about black and white, and we also wanted to point out that our entire perceptual system is based on context. In fact, I'll get to that with this in a second. There's a reason for this. So I told you I dress up my clothes based on my perception lecture. So we're going to do that. But this S here, the text here, is actually this one over here. And this is this really dark one. It's all relative because your eyes are moving around constantly. And Tufty being Tufty, loving the big hyperbole, big sky is falling phrases. Avoid catastrophe becomes the first principle of bringing color into information. Above all, do no harm. He doesn't mix words. If you're going to put color in, make sure you're doing it for a reason. You have to be thoughtful about it. And what we're going to look at today is the take-home lesson at the end is like, no, if you're going to put color, do it intentionally. Don't do it just whatever. Do it with purpose. Do it with some intentionality. Here's the other thing. Computer science ruins the world. I love hyperbole as well. If you've done anything with me in my classes, for example, 1400, maybe you've purged that from your head. But we talked about RGB before, red, green, blue. It's a way of encoding it with a byte of information, a byte of information, a byte of information. If we have transparency, you have another byte of information. We have 4 bytes of information to encode one color. So each pixel could be, you can represent with 4 bytes of information. Is it a byte? I think it's a byte. Yeah, 255. So the red value is 0 to 255. The green value is 0 to 255. It's how we're encoding the data as bits. That's why it looks like that. That's why we had to learn binary in 1400. And it's completely stupid. I say this as someone that actually worked in this space for a long period of time. And, you can do all sorts of crazy math tricks. And I had my former boss was like, oh yeah, just the distance between 2 colors is how much of a difference of the colors it is. Except your eyes are not a computer. Your eyes perceive things differently. So this is, I do believe, this is our RGB color wheel right here. So if I have all whites, they go in here, or it might be down here. It will form a cone, but I think it's actually ends up being a cylinder for RGB. If I go 0, 0, 0, I get black. If I go 255, 255, 255, I get white. And I can do changes of red, green, and blue. Except the mapping, you think by increasing the blue by 5, you get 5 times, 5 steps more blue. If I increase green by 5, I get 5 steps more green. But our eye doesn't work that way. Look at this band right here. It's this dead band where you hardly have any granularity, any kind of perceptual granularity. If you look at this green band here, you have a lot more fidelity in here. Fair bit of fidelity here. It doesn't scale linearly. That our eyes don't work that way. We're really good at detecting green. We're really crap at detecting blue. But we can detect when there is some blue, but not the steps in there. And so HSV, so hue saturation value, which is another way of encoding data. It has a bit more granularity. It has a bit more accuracy. But CIE Lab is another way of encoding color. And that's much better because it's based off our perception. And they mapped how people see colors to what the values are. So when you increase it by 2, you get 2 steps in terms of a color. Not just, oh, sometimes it goes up, sometimes it doesn't. So CIE Lab, if you're trying to do color correctly, that's the way to go. But I'm not expecting you guys to be dealing with that stuff. But just be aware that your visual system is not as cut and paste as like, oh, RGB, I'm going to increase it by 5 blues and see something different. You don't necessarily see something different. In fact, it goes really crappy when it gets down to, when it gets to black. It starts getting, the differences in the colors are really hard to distinguish. Because we have rods and cones, some of them are better than others. We have 5% blue cones, rods, blue cones. And rods, we see differences of light intensity. In fact, this is actually what's happening. I find this fascinating. How do you, with rods at least, how do you see color? Well, rods, you can see brightness, lightness, fine. But on top of that, with your 3 sets of cones, if all 3 go off at the same time, you see something as brighter. I know that's somewhat intuitive. So if all 3 red, green, and blue cones go off at the same time, you go, okay, that's bright. If not, if all 3 of them barely go off or don't go off at all, you see it as dark. Well, irrespective of the rods. The rods are something completely different. And so how bright to dark something is based off of those 3 plus the rods. If I have red, but I don't see green, I see red. If I see green, but I don't see red, I see green. I get one or the other, but not both, essentially. So I can see red or I can see green, but I can't see red, green. I have 2 different rods and they're different. And how red something is based off how not green it is or how absolutely red it is, right? So if I don't see any green, I see a lot of red, my red cones are going off, but my green cones are not going off, I said red, right? Glad I said red. If the green cones are going off, but the red cones are not going off, I see green. If they both go off, I actually don't see that at all. I see yellow. And if all of them go off, I start seeing white. It's this what I don't see versus what I do see. It's not a hard-coded number. It's relative to the other colors that I see. Because if I see both red and green go off and no blue, I see yellow. And if I see blue but not red and green, I see blue. So what I get is I don't get reddish green. There is no bluish yellow. There's no yellowish blue. I can't get opponent colors. And that's actually why, if you look at how our color wheel, all our color theory, all the things we do with color, if you did any kind of art background before, all of those theories are based off of how we see. It's ingrained based off of what people have learned, not necessarily the neurology, but the neurology backs up what people have for color theory. That if I have a lot of red and no green, I see red. But if I have a mix of the 2, I just see yellow. And I get this sort of bleed over effect. It's me interpreting based off of one or the other, but not both. Okay. Which means also that I get color constancy the same way that I had with the brightness lightness. That this right here is exactly the same color as this square right down here. And despite having seen this and demoed this, countless times, I still see bright orange down here and dark brown here, despite the fact they are the exact same color. And I pulled it out just because I didn't believe it myself. And I confirmed that. I put I moved the snippet off and cut out just this one little bit, and it is this color, and yet I cannot not see it. This is all relative to the other colors nearby. Which brings us to today's outfit of the day. This jacket, the most impossibly hard to match jacket that I have in my wardrobe. The reason I bring it up is that it is taupe, the most annoying color on the planet. Taupe, in case if you're a francophone, you just say, why is he saying the word mole? It's because it's the color of the fur for a mole, and we just took the French word for mole, right? It is brown gray. And what's weird about this particular jacket is depending on the light, it looks radically different. So in natural light, it looks gray. in like overhead lights and stuff like that looks brown. And so trying to match it with anything during the day is a Herculean task. Well, maybe not Herculean, but it's pain. Because, and I'm sure many of you have the same thing. Many of you have bought something at a store, like an outfit at a store, said, hey, that looks great. You bring it home and it looks extremely different because the lighting in the store is different than what you're lighting in your house. It's all relative. It's all based off of what is reflecting off of it. And also just based off of other things around you. Color is relative. It's not absolute. So in case you are, cursing and swearing at some outfit that you have and the color is not being consistent or hard to match on it, you can blame your visual processing system and how your eyes jitter around. So we looked at simultaneous contrast. You get the same thing here. But the difference is, look how bright the screen is, look how dark the screen is, and it's the same green. And even if you know that, it looks different. It is the exact same green, but you will get this color shift every single time. The nearby colors influence what you see. In fact, that's the problem with, again, this jacket. I put, black with it. It looks different than if I put brown with it or I put gray with it. I will see different things depending on what goes next to it. And that becomes part of the art form of, fashion, but an art form that I'm blissfully unaware of. All right. I say that expression too often, but again, and now it looks like a different block. But even then, this side looks darker than this side, despite the fact that we know it's the same color. The nearby surroundings change things. This X, this line here, is the exact same color for the left and the right, despite the fact, and you know it because it's right down here, despite the fact that it looks like it's yellow, and then this side it looks like it's purple, because it's all relative. And then I can get, so this is what's called simultaneous contrast. We will see things differently depending on the nearby surroundings. Like this looks like a very bright red X. This looks like a very dark red X, and yet it's the exact same color for both. The squares are the exact same. It's just I filled in the yellow, the white blocks here on this X, and I filled in the green ones over here. So what I get is a different perception. This actually gives us the Bezold spreading effect. So if I intersperse little bits of color together, they merge without me wanting to even. So I see this as a dark red pattern because of the black all around it. I see this as a brighter red pattern because of the white all around it. Because the nearby colors bleed over into it. You can't help it. Which gives us interesting things. Like if I put scatter plot, do I put a black border around it? It will change the perception of color. If I have a whole bunch of colors nearby each other, it will change the perception of color. So if I have a legend and I'm saying it's peach, let's say, as the color, and on the scatter plot it might look different because the nearby colors will influence how I see it. My ability to read this table will change. And it's just something to make sure you're acutely aware of. Does it look the same on the scatter plot as over there? Does it look consistent? Choosing what colors you're using. That's why you can't have a whole bunch of crazy colors, because we're not very good at differentiating them. Oh, and this, at least I perceive, looks smaller than this. You get this sort of, but it definitely these definitely look darker than this. You also get a large red area versus a large green area. What looks bigger? I think this looks considerably bigger. But it's, again, it's a perceptual factor. You have to be playing around with it. The areas are actually equal. And if I choose the same luminance for both colors and they're just a little bit off from one another, it looks about the same, despite the fact this looks bigger because we're good at seeing red. So here's our vocabulary, our normal vocabulary. We have luminance, that is brightness to lightness, right? So white to black, that's our luminance value. How bright something is. Nothing to do with the color. What we call color, we would normally refer to as hue. These are our rainbow colors. These distinctly different colors that we say. And they are also contextual. They are also, that's what I'm looking for. They are culturally based. to a certain extent. Most cultures have most of these rainbow colors. Some cultures have a couple extra ones in there that they will actually see, and they will see the world differently. And their language matches that, and their ability, their perceptual ability matches that. It's wild. If anyone here speaks Russian, that would be an example. The Russian language has a light blue and a blue as different colors, and people will identify them as different colors. They will see the spectrum of the rainbow differently than most other cultures as a result. I think English, it gets a little weird, but we have mauve and purple. They are the same color, really, but one's really a lot lighter. And we often will distinctly distinguish between them. Pink and red. Pink is just white on red with some red, but yet we see it differently. We will identify it differently. There's a cultural component as well. But it's important to know what the cultural connotations are. It's important to know how the culture looks at different colors differently. Like what green is for some culture is very different than green in another culture. And saturation, however, is how much the brightness stays the same, the hue stays the same, the amount of other merging colors, the sort of the mixed upness of it changes. So what you would ideally expect for different saturations is the perceived brightness of the color is the same, but if I add the other colors, it looks sort of bleached out, like a well-washed item. That's what saturation, when I have a higher saturation, it has that intensity. Low saturation has sort of the washed out look to it. And I can manipulate color that way. It's another dimension I can manipulate color with. Luminance, saturation, hue, and they're distinctly different. Because luminance, I can use my rods and cones on. Hue, I don't. They're purely based off of my cones. And it will also be looked at in a different visual processing system. So this is not as effective as I wanted it to be. It's hard to read, and supposedly you guys have teachers that actually give you this kind of crap, but oh my God, I'm sorry for this. If you look at this thing, and let me try and read it. Imagine yourself staring at a PowerPoint presentation with this color combo. Does it make you want to scream? Does it feel like your eyes are going to bleed? Blue on top of red, and even green on top of red, has an amazing effect. It makes the text look like it's vibrating. This is not perfect because my screen's vibrated, by the way. Our eyes want to make the blue recess and the red pop out. Then we want to make the blue pop out and the red recess. The phenomenon is called chromostereopsis. And it is enough to drive a person insane. So don't ever design blue on or green on red, ever. It's not just the blue and the green. Just the luminance of both those colors. And that's what's hard to do, to get it exactly right. The luminance values between the blue and the red, if they're exactly the same, you can't read it, or you have a really hard time reading it. But if I have blue and red and they're extremely different colors, if I have a dark red and a bright blue, I can read it just fine. Yeah. Spider-Man's, but you're not supposed to see necessarily the outline of Spider-Man's costume. You don't, as in other words, Spider-Man written in red text on blue background. Because then, yeah, he would be wrong. And why do you think he went to the black costume? I mean, really, it wasn't for, because it was the 80s and he was trying to look cooler. No, it was purely for this. Because this is what we have. This is how my friend Rangi, yes, his name is Rangi, sees the world. He was a visual designer at CD Adapco. So the other visual designer had this same problem. It's how he sees the world. Not exactly, but this is the closest approximation I can give you guys. He would literally complain when he would go out with his family to do this. And it's a weird concept. He would be just reaching into a plant and just grabbing randomly, because this is what they were doing. They were picking strawberries, and he's guessing at where the strawberries are. He's just putting his hands in and pulling off random berries and hoping to God they're ripe. He can't see when a strawberry was ripe or not. It was a guess. Now, he could see if it was whiter, like here, You could see that like a slap in the face. But the actual strawberries themselves were not popping in the leaf. You could tell when they were completely unripe because they were white. And as soon as they went ripe, he couldn't see it from the background, which is, kind of wild because he's red green colorblind. It's 5% of the male population. It's a huge number. It's not something to just to thumb your nose at or to ignore. It's also something perfectly normal. It's just there's some ridiculous large number of the percent of the population that are stereo blind. They do not. I think my wife has that. She had trouble with her driving test for one of the dimensions of stereopsis, being able to see with two eyes. She sees with two eyes, but one of her visual cues for it, she was blissfully unaware. I keep on saying it. She was completely unaware. There you go. She's completely unaware that she couldn't see some part of stereo, with both eyes. And you can live your entire life not knowing that you have this as a problem. And so, but then the question is, why do we see red so well? And people go fruit, we said blood, we said a bunch of things. But then the question is, do we need to actually, how do I want to say this? If you're looking for fruit, you need to identify fruit. You also potentially need to grab for it, but you can just see the basic shape. Once you identify the fruit, you're fine. You can grab the basic shape. What we end up getting is this sort of thing. We actually have two visual processing systems. One that goes to the top, the dorsal visual processing system, and that should be the ventral one, goes along the side. It turns out you're predominantly, if you want to think of it as sort of quick and dirty terms, if you will, your ability to see brightness, lightness goes up. It also goes up here around where your motor cortex is. This is where all your feeling, but also how you coordinate your body is. It's up around the top part of your head. So sight up to the top. It's great for when you need to grab something.
Yeah, exactly.
Me grabbing a glass, knowing where it is, I'm using shape. That shape is based on lightness to darkness. And you can actually, if you have no lightness to darkness, it's actually hard to grab a shape and pick it up. If you just have color, but the luminance is the same, it's actually hard to see. Going to the top. The rods are king there.
Oh, and Monday's the day off in Canada.
And down here, where it goes to your temporal lobe, where you're coming up with words and speech and all your language parts, that's where color is going.
Yeah.
When I want to identify particular items. Now, this is very, very generalized, and there's a lot more devil in the details here, but think of it as color is there for me to identify different things. They're great for identifying or categorizing things. Color with hue. Brightness and lightness is for shape. And that's why this is a pain. Because my ability to read is based on the shape. It's up here. Saying the words, but I still read that I'm reading the outlines of the shapes with brightness to lightness. And if I don't have that difference, I don't see the word. I just see a blob of color. The color sort of blends in with the rest of it. So what ends up happening is my ability to read text is based off of brightness to darkness. And if I have two bright colors on top of it or two dark colors on top, I can't read it, even if the colors are different, even if the hues are different. I'll see that there is a difference, but I won't see the shape. But if I want to identify things as different, as categorically different, I want to use color. I want to use hue. So by the way, let's go over some of the basic types of color blindness. Here would be an image for someone that does not have any form of color blindness. And I'm sorry if I'm the terminology, some people get offended by certain terminology and stuff like that. Normal, I guess, visually typical, whatever the case is you want to use. But this is what the original image is. Pretty plant, right? If my rods and cones are working correctly, I should see like a bunch of really bright colors. They're very weird looking colors, by the way, and sort of a blue-green background here. Distinctly chosen just to show off. the normal red-green color blindness. If I'm a protanope, so I've faulty red cones, and then I have deuteranopes, faulty green cones. Here is faulty red cones. It looks blue. The reds are not popping out at all. It just looks blue. Here is faulty green. Let's remember, this is based off of the difference between red and green. That's how I see red. That's how I see green. And so if I don't see one of the two of them, I get this sort of thing. It's a bit odd, but I mean, you can't tell what another person sees, right? I don't know I have these giant blind spots in my eyes. But this is what you would have if you're red-green colorblind for red-green. So either protanopes or deuteranopes. If you were, that's the 5% of the male population. I think it's the protanopes actually in particular. That's the 5%, the really common one. Tritonopes, faulty blue cones, are much, much rarer. It's like a 0.1% of the population. But you still need to worry about it. This is where accessibility comes in. When you're designing a visualization, when you're designing a user interface, you can't just ignore it. You got to be aware of it. So I would like to point out, again, the visual designers at CD Adaptgo, 2 out of the 3 of us, I was the only one that had normal color vision. The other 2 were red-green colorblind. One of them did not know he was red-green colorblind. They decided to make a highlight color for parts in their visualization that was this like fuchsia. It was slapping. It was really obnoxiously bright, like extremely bright. And it was this weird fuchsia color, intentionally chosen to make sure that it didn't match any other colors and it was stand out as a highlight. They searched long and hard to get this thing. And they do demonstrations, and the 2 other designers would be like, "So what are you highlighting there?" And they're like, "What do you mean? What are we highlighting?" It's a bright fuchsia thing on top of their system. They're like, "Yeah, we don't see it." And one of them, Blitzplant, would not admit that he cannot see this bright fuchsia on top of this because he couldn't see that. You cannot assume that everyone sees colors the same way. So what you want is that difference of luminance, at least a little bit of difference in luminance, so you can actually see this. You can still see the flowers here. They're still very nice looking flowers. You need to make sure your visualization still works for people that are red-green colorblind. Here's what a tritanope looks like. It's the blues sort of blend in with everything else. Okay. So this is what the rainbow scale looks like. Here's what a protanope sees. Here's what a deuteranope sees. We're not even doing the tritanope. And here's what the lightness looks like. It's why we hate rainbow color maps. Look at this thing. Here are all my hues. If I'm completely colorblind, if just purely based on lightness, it looks about the same all across the board. And if I'm a deuteranope or a protanope, it's kind of hard to distinguish them. Textures, which is good for hunting camouflage prey. Interesting. Well, at least that's a hypothesis. Very much like the Born to Run hypothesis that people were designed to be the best in the world endurance runners, which I question sometimes. But yeah, there's a bunch of things like you have to sort of try and explain why certain things are in the population. It's also recessive. So women could easily pass it on to their male progeny, but it doesn't prevent them from having kids. It doesn't really necessarily take up the males of the population. Males of the population, if they're hunting, you're assuming a hunter-gatherer sort of breakdown of the gender that way. The people that need to be able to pick out a berry would be the women, if that's what your society is doing. There's a bunch of different reasons. It's not brutal in terms of survivability. It just to the point that people don't notice most of the time. It's just modern society. A lot of people assume that people see that color, and you can't make that assumption. It's a great point. Thanks. So yeah, if you can't see these, you may have a problem. It's weird when you meet someone. I've met lots of people doing experiments where you say, okay, well, what's this number here? And they go, what number? You're like, what do you mean, what number? And they just don't see it. And it's surprising because you wouldn't notice otherwise. This is why we say get it right in black and white, because this is what this looks like when I go black and white with the same image. Not only is it a garbage visualization, I think it was designed to be just to be a garbage visualization. I can't think of it being out in the wild, but in black and white, it looks like this. And if you don't see one of these colors, you have no clue which one of these things is right. That's why we do it. That's why we have to worry about this. So if you do it right, so this is what you do when you do it wrong. Here's a rainbow color map on an artery. Here's what it looks like in black and white. If you're red green colorblind, you could still be a surgeon. You should still be allowed to be a surgeon, and yet you can't see things here. The rates wouldn't be so high without some evolutionary advantage. Not necessarily advantage. Well, though, yeah, you could say high. But then again, you'd think redheads would die out of the population as well as I guess, former redhead. But as a redhead, yeah, they're still around. You would think that it's a recessive trait and it's not necessarily helping you at all. Yeah, there's a whole bunch of things. It's hard to infer things about evolutionary advantages in retrospect, but it's 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 fun to look into it. It's just we don't have any definitive one way or the other proof yet. By the way, if we're doing this, this is Michelle Borkin's later thing, and we're going to look at it again in a second. But this is the remapping of the same artery instead of using a rainbow color map. Because if you go into black and white, you do still see the differences. It's just not, it may be not as obnoxious, but down here, for example, it still looks like a very problematic area. There would be warming in New York City. If I go to black and white, I still can read the bar chart. The last thing you want is, if you go to black and white, because by the way, I'm looking at your visualization with a black and white thing. So in case you don't think, if you're not worried about accessibility, maybe worry about your grade. All right, I'm still looking at your visualization in black and white. Just check, print it black and white or print it off or whatever the case is, just to make sure it works. Here would be, here is the amount of heat accumulation in various parts. But notice again, it doesn't have to be extreme. You could still keep color in there. This red still pops. This beige still stands out. But when I go to black and white, I can still see the different layers. I just don't want them isoluminant. I don't want the same luminance, isoluminant. I don't want them the same brightness level. I need a little bit of variance on it. So getting it right in black and white. All right. By the way, in case you're wondering, you can check BizCheck is one of them. I think I have a bunch of other ones as well, actually. There's a slew, and we're going to go over a couple other ones afterwards. There's a slew of online websites that allow you to check, to take a screen capture of your visualization, throw it into this thing, see if it works. So, by the way, yes, we have another example of why you need to worry about brightness and lightness. Here's another example right here. Try and read that. It's color perception 2 is what I've written down there, but I had to stare at this for a long time. And notice if I just have black, it's sort of, sometimes the S is obvious, the A is obvious, but there's some other characters in here that don't work as well. Right here, right as soon as it hits the black part. Okay. But if I have a background around it, I can read it just fine because the nearby colors compared to this, I'm reading based on luminance, not based off of just purely what the color is that the text is. So that C is really hard to read because the background is dark, the C is dark, and there's a problem. All right. So here's Matplotlib's visualization options, right, for the various ways of mapping out colors. By the way, don't use this one unless you really have to. That's the one we're trying to force you, tell you not to use, right? We have HSV, we have rainbow. There's a bunch of these things. And there's divergent color maps. You do not have to make up your own color maps. D3 and Vega Light both have this, and they also use sane defaults. But if you don't want to use the sane defaults, you can always use other defaults. You don't have to reinvent the wheel and figure out your own color mapping. So people have already looked at all this stuff. But this is what I want to point out. Remember last time around, we were looking at these arteries. I said, here's rainbow color map, and I did the rainbow color maps with a bunch of these arteries laid out like this, flattened. And I said 61%, it goes from 39 to 66% or something like that for be able to see problematic areas of the heart. If I convert to this color map instead of this rainbow color map, this is a saturation-based scale for my color map. And the accuracy for finding heart conditions is 91% now, from 39. They're looking at my heart to see if I'm going to have a heart attack. I want this one, thank you very much. If someone's looking at my heart, I want to be able to determine, I want the doctor to be able to find the problem. That's why it's important. It's not just, well, we think we the colors. No, it makes a difference in people's lives. It prevents people from dying. That's why we do what we do. Okay. And even if you go to black and white, it still works. If you're a doctor with recurring color blindness, you can still use this thing. It may not be as accurate, not be as easy to use, but you can still use it. You've already been working around this problem for your entire life. Like everyone, I mean, almost everyone here probably has some issue that you've been working around your entire life. I know I have my issues. So why are rainbow color maps crap? I'm just going to say they're crap. Well, there's no perceptual ordering. We'll look at that in a second. There's no luminance variance or very little luminance variance. So you don't get brightness to darkness. It's just hue. And you see a sharp transition as soon as the color changes. And you have no choice but to see it. It's very frustrating. It's very misleading as well. So I know that this is right. Black to white. Great. I know this is out of order now. Fine. I can tell this. Which one is which? Is it yellow green or is it green yellow? Which you may know. Did you have to think about it? That's the question. Does it automatically happen for you? Or did you have to think about it? If you had to think about it, it means you shouldn't be using it. Like if I had, and I literally had to reverse engineer this and go like, okay, how do I see yellow? I see yellow by basis of red and green at the same time. So therefore yellow must be in between the red and the green. And I can't do greeny red. So I have to have a color in between. I had to cognitively reason about the order of my rainbow. And if you ask people, and they've done the studies, people do not naturally see rainbow. Like they do not know the ordering of a rainbow. They have to think about it and they go, then it's blue, then it's, They have to think long and hard about it. It's not natural. Your perceptual system thinks of them as categorical data, whether you want to or not. So, and here's the notion of the perceived sharp transitions. This is sort of a wavy kind of brightness to darkness. There's some banding, fine. Now look at this. This is distinct. Each one of these things are very, very distinct versus this is part of the overall pattern. It looks like completely different data here. I'll go even more extreme. This one's my personal favorite. Here's what the actual data looks like. Here it is with a divergent, we have a color mapping. It goes through yellow, the yellow reddish areas, but it goes from white to black. So you get this nice little curve transition here. You will see a trend, like a banding here, whether you want to or not, but it's not really that bad. Look at this thing. I see 1, 2, 3, 4, 5, 6 areas. I will only see those 6 areas. I do not see anything other than those 6 areas. I see a whole bunch of different areas right here. If this is a continual data range, it is just going from this number here, like continuously up. And I see a bunch of bands which do not actually exist. There's no banding there. This is just because I mapped it to a rainbow color map. That's why you can't use it. Or if you use it, you have to be very, very careful, because if you use a rainbow color map, you will see banding whether you want to or not. You cannot turn that off from your head. Here's red to green going through a center point. Still, you see a very distinct this chunk, this chunk, this chunk, this chunk, like sides. The choice of color will actually influence how you actually see things, how you see the data. And also, by the way, if you want to use 2 different dimensions at once, good luck to you. It is damn hard. So here is one of the few kinds of color maps that you use bivariant. So with low in both dimensions here, high in both dimensions here, high in one dimension here, high in one dimension here, it's really hard to read these things. It's very, very, very difficult to design. I would strongly recommend against using it at all. And it's completely to make it colorblind friendly and intelligible and efficient. Not only is it hard, it's next to impossible. I would say don't even bother trying. Okay, so we have three different types of categories of information. We have categorical data. Hue is fantastic for that. So rainbows, great, go for it. Rainbow color maps, right? Because they're perceived differently, they're perceived distinctly. Hue is great. So there's no magnitude difference between them. Red versus a green, it's just red and green. Okay, that's why maps are colored that way. They're distinct hues. Sequential or ordinal data. So I can use saturation, I can use luminance. Both of them work really well for that. You can even use continuous data for sequential, like you can do from like white to green. That'd be fine, but it's hard to read off exact numbers with any kind of color. But ordinal, wonderful, right? Halfway point. I don't know what the number is, but I know it's halfway. And then there's one other version. So I have sequential. I can go from white to black or white to green. I can go from black to green. I can go from very unsaturated to very saturated colors. I can go from, yeah, those are the big ones, right? Brightness and saturation are the big things for me. Divergent color maps are useful in certain cases when I have a distinct midpoint. So the students that fail, the students that pass the course, there's a distinct midpoint. It doesn't have to be 0, but there's a distinct midpoint. So I want to emphasize where that midpoint is and what the two ranges are. So let's see an example of that. Oh, well, I'm getting myself here. So here are my 3 different ways of doing color encoding. If I have a color map for categorical data, hue is just fine. And then I have to worry about sequential versus divergent, where there's a midpoint and go different directions. The integer colors, the integer numbers are diverging. I have a center point, 0. It goes off in infinity in both directions. Sequential is the whole numbers, right? It starts at 0, goes off. So here is color map using the worst, our friend and yours, my friend and yours, rainbow color map. Very useful. Useful data set, huh? Here's what it looks like in real life. I have a center point, and I go from blue to green, 2 different colors. So I know where the center point is. There's a clear distinction because it's the coastline. It's where the sea level is. That makes sense, right? And so darker blue as you go deeper into the ocean, it's sort of a natural mapping here. And you go lighter as you go higher elevation, like snow-capped mountain. Fine. It happens to be a nice choice of color map in this case. But the point is, divergent is I have 2 sequences going in opposite directions, and they don't relate to one another. Here's what a divergent color map looks like. And notice that the sequential color map, all of my mapping, the vast majority of this is right around 500 to negative 500, which is pretty much the entire United States of America and parts of the sea level. And it just, you will see this band right here where the green is, which may be nothing at all. It's this thing right here, I think. That's not that important to you. I want to know where Florida is versus the ocean. And I want to know where certain mountain ranges are. That's why we do divergent. So here are the other ones that you can look at. You can look at Color Brewer. If you want to look at different color scales you can use. Although again, D3 and Vega Light have them built in. Categorical allows you to play around with various color maps and stuff like that. So if you want to make your own color maps, again, you can use the default ones for the most part. And here's my summary. If you talk to any interior designer, any artist, they will tell you about this sort of thing. They may not be using the same reasoning, but they say the same thing, and I ignored them for years and years. The reason why you have like one yellow chair, because the only way to get a pop out effect is to mute everything else. So you want to control pop out effects, low saturate everything else. You don't want a whole lot of ultra saturated colors because you won't know the signal from the noise. You're trying to avoid cut up color and competing colors. You want neutral backgrounds to control how the impact of the color is. And you want to minimize the amount of simultaneous contrast so you don't just like blow people away with just bright saturated colors everywhere. Because people are staring at this and it's a lot to take in. So use Color Brewer, use some other system if you want to look at different scales. You can look at the different scales in D3 or Vega Light. That would also be great. You don't want to forget about aesthetics. We're not testing you on aesthetics. But the big thing is you don't want to just dump color at people. You're trying to control what people's eyes are going to. And only way to do that is to mute everything else and have one thing stand out. Page more illusions, everyone's favorite, right? I still don't see the white and gold version of it. I cannot see it. I honestly can't. I've been trying for years now. I only see the black and blue dress here. Some of you will see it as white and gold. I don't get it. I think you guys are all yanking my chain here. But some people say that they only, it's a weird phenomenon. People can do wars over this damn dress. Just from one overexposed photo. Because the issue is, depending on what the light is in the background, it's either a gold and white dress with a blue coloring in the background or a blue light, or it's a black and blue dress with a sort of a yellow light in the background. And that, again, color is all relative to your eyes. And since there's no other additional information, that's why you get this particular phenomenon. And of course, I think I like the rolling ball one that you guys gave me as an example. This or this, right? Because the actual pattern that we're looking at, while we look at something on the periphery, our ability to see things with a whole bunch of different luminance values gives us this illusion of movement because our eyes are moving around. Okay. And I like pointing this out. So let's see if I can get it. This is, so for my Northeastern class, this is so many, many years ago when I did this, I gave them a challenge. They were doing, this is for a non-programmers class in how to use a computer essentially. So we're using Excel, we're using Access. We're learning just very basics of computers. Some we get into a little bit more detail in there. But the challenge I made for people doing Excel, because there was no reason to, they're learning how to make a chart or a graph, and it like you go over here and change this thing, and they're not going to remember that. So my challenge was make the ugliest image you possibly can. If you do that, you will know how to make a graph. You will know how to change all those settings. So let's have a look at the ugliest things that they could come up with. Okay, so that's pretty terrible. Notice the ultra saturation, and notice that the color of the text is the same as the color of the background, so you can't read it. Same data set for all of these, by the way. That's, by the way, the president of the university, Principal Ione, and possible to read text with this background, a 3D chart line graph with this extreme angle to it, so you can't actually read it and you get a horrible occlusion. Nice. There's a bunch of Principal Ione things. This is just a dump of all the graph, what we're using yellow as a background, and the same luminance value text on it, so you can't read anything. And it's the ISOR on, because why not? And another ugly ISOR on. The occlusion is just the problem in that one. Okay, and then we just have a whole bunch of really fat lines that you can't see anything at all. I didn't even know you could do this. The bar chart, we're doing that. Okay, yeah. These are terrible. I'm going to blow through. I didn't know you could do that with Hawks. You can do bar charts with rubber duckies, it turns out. So good for them. I'm just going to blow through a lot of these. Here you go. We can come up with a lot of ugly stuff. The act of you
Yeah.
making something that's truly, truly terrible will tell you what to do, how to do things the right way a lot of times. Like this.
Social skills so that
They knew that I hated 3D pie charts and random backgrounds. That's not so bad. It's just, well, it's 3D. Oh, there you go. I'll leave it at that one. Okay.
and then it's a hate love relationship. So one day they hate each other, the next day
So
they love
let's see if I
each other.
have anything else in
They
here.
do spend a lot
So
of time
for normal
together.
rules, we want to avoid vivid colors.
Difficult on
They guide attention. So you need a pop-out effect. So you got to use them sparingly. Excessive amount, perceived as unpleasant or overwhelming, and quite frankly, you don't see anything. If everything is grabbing your attention, nothing's grabbing your attention. Foreground colors should be separate the work from the background. So brighter in the front, muted in the back. Colors should communicate better if they offer simultaneous hue and saturation and lightness. So if you change a bunch of things at once, they stand out better. And low light and steps can be small. So and low light, the low end of things, small steps are can be very. It should be small. High end requires larger steps. So it's called Weber's law. So if you have a very bright red, you need an extremely bright red to distinguish it from the other one. Discrimination is poor for smaller objects, and so you need to be careful about that. If you have small little things, your ability to see the color is going to be reduced. Complementary opponent colors have the highest contrast, so you can use that to your advantage. Some hues appear more saturated than others. We didn't talk about this, but yellow is the least number of perceived saturation steps. The difference distinguishing the different colors of yellow is the hardest, but it also is considered the brightest. The brightest lights fall in the yellow range, while blues and violets and reds are the least bright in terms of what you perceive as bright. But yellow, you have the fewest amount of granularity in the colors. For labeling, you want black, white, or gray. You want at most 4 colors, 4 secondary colors, and the number of colors you have in total should be less than 7, generally. Warm colors excite emotions and grab attention. They always say that. I'm not a big fan of like how do you feel about your colors? But bright colors are more for grabbing attention, and sort of the more cooler colors are sort of more relaxing. And if you increase lightness, or the saturation, you do not change the hue. So that's a thing you can play with. Objects of similar hue are perceived as the same, even if they're not. So if I have 2 different blue bars, 2 different saturation levels, and then I have a bunch of other colors, I will perceive those blue bars as being connected, even if they're not connected. And that's a dangerous thing. So a world map sort of works around this by being very explicit about it. But if I have only 2 blue bars and everything else is a bunch of different hues, I will think there's a connection, even if there's none there. Thing to be on the lookout for. Okay. And if you want a real world example, this is actually what NASA is doing. I didn't know this, so I always found it fascinating. They actually Photoshop all their images. I thought they were just raw natural images. No, they're Photoshopping them. The idea is they take something from the Hubble telescope, and then they change the background, change a little bit of the colors of the foreground, because quite frankly, you're not actually seeing this anyways in the real world. You're seeing a snippet of the spectrum anyways. And so what they do is they mute around the outside, so you get this pop-out halo effect. And so this is what you're seeing right here, because it allows you to see the details of this separated from the back, so you know exactly what you're looking at. Oh, wow, perfect timing. So next time around, when we come back next time, next class at least, I'll just see if I can get it up here. That sounded terrible. All right. Here's what we're doing next time around. We're going to be looking at cognition and how we actually detect patterns and how we control attention. So we do have one more lecture at least on, the psych part of this course before we go back right back into visualization stuff. But when we come back, we're going to take a little mini break here. And when we come back at about 5:10, we'll have a snack or whatever you need to do. When we come back at 5:10, we'll start the lab. And all we're doing, I have a, how did I frame this? The Vega Light Lab, it's a, a dress rehearsal. We're doing it live. We're doing the lab where I made it relatively quick. If there's something wrong with it, please ask. It's a rush thing, but I've never run this lab before. So the lab that you see online right now in the lab So You Learn course is links to Vega Light and has a bunch of instructions step by step on how to make a visualization in Vega Light. And we'll see the difference between the two of those, two different approaches between V3 and Vega Light. Vega Light it cuts out a lot of the cruft, but it also means you have less control over things. But for our sake, I think it works relatively well. So what we'll do next time around, or 10 minutes time, is we're going to be looking at Vega Light and how to program so to help with the next homework. All right. Thank you, everyone. I'm going to mute my microphone because my son's about to start talking to me, and I'm going to go grab myself a snack, and we'll be back at about 10:05. Thanks, everyone.